This is my natural base.
It was really low.
Okay. Now, welcome back.
I'm not uploading the person.
All right. So, yeah, now it's swiveling. All right, let's see how you did. You look at this graph. This is a graph of f prime. You are properly trained now, right? When you see the derivative being above 0, we know that that's where the function is increasing. So this is from negative 3 to 0. So did you put a negative 3 and a 0 bracket? Yes. Oops, wrong spot. It's increasing on negative 3 to 0 because f prime is greater than 0. Okay? And this is where the issue comes in. Yes? Now, the technical official answer that you don't need to put on the AP exam is this. Because f prime is greater than 0 on negative 3 to 0, this way. Okay? I'm going to try to explain this today. Why there's a bracket there, even though f prime is equal to 0 here. Okay? All right, then this part here, f is decreasing on 0 to 3 with a bracket because f prime is greater than 0, technically on 0 to 3 with parentheses. Less than 0. Boy. Jamie, can you come with me the rest of the day? Just follow me along and correct me. I'm going to need it today. All right. So I'm going to try to explain why there's the bracket. Okay? So what I have is a really big ladder. Okay, follow me. Okay. It's like one of those old slapstick movies. Okay. All right, here's my demonstration as to why those are brackets, not parentheses. Okay? So I have the graph of the derivative, you can see there, and I have the graph of the actual function, okay, or one of the functions, because remember, there's an infinite number of functions whose derivative is this. They only differ by the constant that shifts them up or down. Okay? So we said back there that f, which is the blue one, is increasing on the interval from negative 3, which is this dot, all the way up to this dot, and I put brackets on it. Okay? So let me try to explain why with the ladder. Okay? Now, if I climb the ladder, okay, you could say that I'm increasing. Right? So I take a step, I'm increasing, I'm going up the ladder. Okay? Take another step, I'm increasing. This is a really old ladder, so make sure you got 911 ready. Now, how high can I go? Higher than I should. I think we're good. Can only tilt so far. Now, how high can I go? I can go all the way up to the top, right? And step.
You can, but you'll hear.
I'm not going to stand on there, though. It's a fear here. Okay?
Are you afraid of heights?
Yes.
I think he's more afraid of unstable ladders.
Now, listen carefully. I asked how high can I go, and you said I can go up one more step, right? And that means I have to go all the way up to the top of the step. Okay? That's why there's a dot at the top. How far does it increase it? It increases all the way up to the top. You see, if you put a circle there, an open circle, or a parentheses, then you're not allowing me to go all the way up to the top. You're letting me do this. And I just hover. But I don't get to go all the way up to the top. See what I'm saying? Bracket, I get to go to the top step, which means I get to go to the top of the graph. If I put a parentheses, I don't get to go to the top. And you're telling me I'm only increasing up to, but not including the top step. Make sense? Now, on my way down, okay, why is there a bracket on the way down? For the same reason. I have to start somewhere, and that means I would start at the top. Okay? Imagine me standing on the top, okay? And I say, when am I decreasing? I'm going to be decreasing. I have to start somewhere, and the place that I start is at the top. That's why there's a bracket on this one right here, because it's decreasing starting at the top. And how far do I get to decrease? All the way until I hit the bottom. Does that make sense? Okay, it's increasing all the way from here to here. That's why there's brackets. And it's decreasing all the way from here to here, because you have to be allowed to take the first step and the last step. Sound good? Okay, put the ladder away. All right, you have a homework assignment, page 169, that's going to be due tomorrow. Okay, and I'm moving on today. We're going to take a look at section 3.2. So take out your notebook. And we're going to do 2 rules today. 2 big rules. So this is section 3.2. And it's Rolle's theorem and mean value theorem. So we're going to take a look at each of these one at a time. So let's do Rolle's theorem first. This is going to be one of those times where I give you a big theorem and then you have to figure out what it means. So Rolle's theorem. And here's what Rolle's theorem says. Let f be continuous on the closed interval. This orange is dying. So let f be continuous on the closed interval from a to b and differentiable on the open interval a to b. Then if f of A equals f of B, then there is at least one number we'll call it C in the interval from A to B such that blank. Go figure it out. Read it and weep. Read it and figure it out. Might find a sketch might be helpful. Okay, anybody got an answer for the one on the board? Kendra, you got something? Okay, really, really close. What do you got?
I was going to guess that f prime of c is equal to 0.
That's it. Okay, there's the subtle difference. The answer is f prime of c is equal to 0. Okay, this is Rolle's theorem. There was a guy by the name of Rolle who lived in the 1600s, and he actually was a disser of calculus. He thought it was bogus. Actually, he thought it produced inaccurate results and all this. But then, actually, the more he studied it, the more he's like, oh yeah, that's kind of good. It's kind of cool. So he came to appreciate the value of it. And so then he actually made a theorem that goes along with it, and we still study it today. So let's analyze this. F is continuous on the closed interval and differentiable on the open interval. So what does this look like? So let's just make something up. When we don't know what it is, we just start drawing. Okay? That's okay. So I've got some function, And I'm going to only look at this right here. Function is continuous here and differentiable here. If I make a smooth graph, then I'm good. So this satisfies this. Uh-oh. F of A has to equal F of B. So this graph is no longer good. Okay? It turns out that F of A has to equal F of B. So I can't do this. I have to do, I don't know, something like this, whatever. It has to go from here to here. This function has to be continuous and it has to be differentiable. And these two values have to be the same. Rolle said this: under these circumstances, I don't care what the function looks like, there has to be a place where the slope is equal to 0. In this case, there's two of them. There's this one right here. There's a c value that works because here f prime of c is equal to 0. And another one over here where f prime of c is equal to 0. Okay? This one happens to have two of them. If you ever try to draw a function that was continuous and differentiable on the intervals, like they said, it's impossible to draw one that starts and stops at the same value, and there's never a derivative that's 0. There's never a slope of 0 that ever exists. It's impossible. Yes? Awesome. So this one here, okay, is the slope ever 0? So it seems like we got something. Problem is the function's not differentiable. So your thinking is right. It's just that this one doesn't work because of the fact that it's not the function, it doesn't satisfy the initial conditions. Does that make sense? Okay, this is Rolle. Now, do you see where Kendra was going with it? She says there had to be an extrema, saying that there's a maximum or a minimum. Okay, backboard. Brand new theorem, mean value theorem. If f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, hey, this sounds like exactly like Rolle's. But then this one says, then there exists a number c in the open interval such that f prime of c is equal to. This one's a little harder because I feel like I don't give you enough information. If you can get this one, this would be pretty awesome. I'll give you a hint. This word comes in handy in understanding what's going on. Brandon might be on fire. Okay, all right, Brandon.
Where f prime of A is less than f prime of C is less than f prime of B.
That's really interesting. F prime of A is less than f prime of C, which is less than f prime of B. I'm trying to think of a counterexample. Can we draw a function? So f of A is the smallest slope. So if I drew this interval right here, this is A, this is B. He's saying if you stick C in the middle, look at the slopes. You see what he's saying? The function is continuous. This is the smallest slope, this is the medium slope, and this is the biggest slope. This works for this example. Okay? Shoot it down. Okay, what about this interval? Does it still satisfy the initial conditions? The initial conditions, yes, it does. But the final one is proven wrong because this is the biggest one then, this is the medium one, and this is the smallest one. Yeah.
Is it then where a point such that f prime of C equals f prime of A times f prime of B divided by 2?
Oh, so close, so close. Divide by 2. You guys saying the same thing. Oh, do you say times? You say times. Okay, you're closer than you. Okay. And you're so close, meaning that there's an average, right? That it's equal to the average, and here's actually how we're going to say it officially. It's f prime of B minus f of B minus f of A over B minus A. Let me explain how this works. And then I'm going to give you a practical example of it. Okay, so this is an answer in a graphical form. Okay. So I have this point A, which is my starting point, and B, which is my ending point. And then it's continuous and differentiable. So I'll make it kind of easy. Okay? We'll just do something like this. And this is F. Okay? So this all satisfies it. Then it says there exists a number C somewhere in AB such that. Now, and this says that f prime of C, which means that f prime of C looks like this. Right? It's the slope of the function at x equals C. Okay? I line those up better. Okay? Is equal to this. What is that thing? It's the slope formula, but what 2 points am I using? I'm using the endpoints. Okay? So the average slope as you go from A to B is this slope right here. Okay? That's the average slope, and that's where you guys were on the right track of. And what this says is that if you find the slope of that line, so let's find the slope of this line. M is equal to. Okay? I need points. Points. What's the coordinates for this point?
1, 2.
starts off with a, and this is the function f, so the y-coordinate is f of a. You see what I'm saying? That's the coordinates of that point. It's a, and then you plug it in the function, and you get f of a. Then, what's this, the coordinates of this point? B, comma, f of b. So what's the slope of the line that connects the two? Well, f of b minus f of a, that's the change in y over the change in x. Okay? Which is what this is here. Now let me try to explain what's going on here. The mean value theorem says that if you got this basic function that's continuous and differentiable, and if you find the average slope, okay, the average slope, then there has to be a point, without a doubt, somewhere in between A and B that the slope is equal to the average slope. Without question, it has to be. Okay? There has to be a point here that it's equal to the slope. And we can prove it by finding the lines that are parallel. Okay? Look at this one. If I find a point, technically on this one, I'd probably say, I'd move my C over to this spot. See this? See that line? It's parallel to this line. That means they have the same slope. So this one has one point, and then I'd say it has another point right here, and then it has a third point right here. This one actually has three places where the instantaneous slope is equal to the average slope.
Would it have to be at an extreme?
No. It can be anywhere. Yes? Exactly. Bingo. That's gold medal worthy. All right. See, Rolle's theorem is taught right along with mean value because mean value is just an extension of Rolle's. Okay? Where the slope is 0. It's exactly the same thing. Now, let me try to explain this in another form. Okay? Practical. Oh, Gunnar?
So the reason that we said it was not correct was because there's no f times a or b, because it's just a point.
Right, because you can't take, well, I think what you guys were saying was take the slope here, add them up, divide by 2.
It would work if we rolled it on the other side of the interval.
Yes. Yes, and here we don't because it's on a closed interval. Here's a practical application. Okay, let's take every summer we take a trip up north to visit our friends who live up near Hayward, and it takes about 5 hours to get there. Okay, 1, 2, 3, 4, 5. And it's about 200 miles to get there. Okay? Okay, so this is 200 miles, and this is 5 hours. Okay? So if I were to plot my trip, I start off at home, and I know that eventually I end up here. Okay? The function that I graph is how far I am away from home at any given moment. Okay? Is it continuous? I hope so. Otherwise, there's a moment where I don't exist. Okay? I'm always some distance from home. Now, based upon the speed that I go, maybe I start off really slow, okay, and then I speed up and I get here. Let's pretend this is the graph of how far I am away from home. Okay? Here's what mean value theorem says. What's my average speed for my trip up north? Okay, it's the line that goes here. What's the slope of that line? 200 divided by 5, which is 4d miles per hour. Okay? Mean value theorem. What does mean value theorem tell me? At some point, I had to have gone 40 miles an hour. Exactly. I had to go exactly 40 miles per hour. Even though sometimes I went slower, sometimes I went faster, the deal is I had to go exactly 40 at some moment. Maybe even more than once. And the chances are I may have gone, like this, but in the end, the deal is I can find a line that's parallel to this, and it's at this moment that I'm going 40 miles per hour. Does that make sense? Think of an airplane taking off, okay, and it takes off. Let's do a rocket ship, okay. A rocket ship that goes really super fast. A little bit goes 45. And so, if it takes off, same deal here. That's the average speed. At some point, the rocket has to be going the average. This is what mean value theorem says. Does that make sense? It's really, if you stop and think about it, it actually makes total sense. Okay. All right, you have now a new assignment, and I'm going to give you a warning. I'm going to be gone tomorrow. I've got a meeting all day tomorrow. So tomorrow's a work day. All right? So, but I'm assigning the next assignment, which is due Friday. So both of them are due Friday now. Page 176 and 169 are due Friday.